And welcome everyone. This is just a pre-stream for today's live stream in terms of the DirectX 12 beginner tutorial. Yeah, the stream is scheduled to start in 5 minutes, so this will be just a pre-stream where I hang out, drink a bit of coffee, and say hello to whomever might tune in. Yeah, since it was scheduled for being in starting in about 4 minutes, we will stick to that schedule. As per always, this is primarily a YouTube feature, which means I won't be checking the Twitch chat as much. Yeah, I hope everyone who followed the other live streams, or at least parts of them, are up to speed, and that everything is going according to plan. I hope I explained things properly in terms of what we are doing, and yeah, just in general, that everything makes sense. Overall, if you look at it, 14 episodes, maybe 12 coding episodes are a handful in terms of code needed to actually get set up in DirectX 12, but we're at the verge of actually rendering stuff to our screen, so yeah, it won't take much longer. And you should basically have all the functionality, at least to get started. There are different improvements to the API that we've created in terms of doing more optimal stuff in terms of rendering. But I think that getting a grasp of the basics in DirectX 12 is pretty important, and yeah, we should spend some time on the basics themselves. All right, we're approaching the start time for this stream here. Let's see. Hopefully the signal is fine. Yeah, looks like we're doing all right in terms of that. I'll just drink my coffee, and then we will get going. An overall outline of what we would like to do is to let's see, outline for the next steps. We want to bind the root signature and pipeline to the GPU. Let me see. right now we initialize is then created, so that's fine and dandy. Um, but we also need to use the pipeline for something, and that something is of course drawing. So we need to do some setup in terms of getting to a state where we can draw stuff. We would like to draw some vertices to our screen, preferably something like a triangle. Therefore, we need to bind uh, a data storage to the pipeline, or rather, uh, uh, yeah, actually to the pipeline, meaning pipeline in general terms, our own API pipeline. And let me see, we actually want to give it a view. Remember that the pipeline state here, I haven't started the video recording themselves, so I'll go over this again, but let's see. If we look at the pipeline here, remember that the input assembler supplies data and the root signature binds different data structures to the pipeline. So right now I'm talking about we want to bind some data to the pipeline so we can do rendering on them. Pipelines do rendering on vertices and potentially indices. So we want to at least bind a vertex buffer, because without vertices we can't do anything. This means that the view should be a vertex buffer view. And remember, a view is just a description in terms of the memory layout and location of the resource. When we bind that pipeline, we can actually start doing draw calls. If we also tell the pipeline how to interpret the data, which means that we need to set the primitive topology, which I haven't talked a lot about, but it's basically how the vertices themselves are handled in terms of grouping. Are we only considering them as individual points? Are they parts of lines, or are they parts of triangles, or lists of triangles, and so forth? So there are different primitive topologies for rendering vertices in general, and we will need to tell the pipeline how to interpret them. Then we set up our pipeline. We could also bind a resource to our single root signature parameter that we created in our standard root signature. Remember, we created a slot for a constant buffer. We don't need that right now, so we will save that for a future video. But yeah, then you could actually do the draw call. Right now, we need to figure out how that draw call will turn out. Yeah, so that's the overall plan. We want to bind the root signature and pipeline itself to the actual GPU slash draw process. We want to bind a data storage to the pipeline slash input assembler here. and give it a view. And then we want to tell the GPU how to interpret the data, and then we want a draw call. Okay, I'm almost done drinking my coffee here. So we will soon be ready to start the actual episode here. But yeah, the coffee is still hot, and I prefer not to drink coffee while we do the actual coding. So we will wait a bit more. Yeah, but I hope that the previous episodes have been um, elaborate enough in terms of giving an introduction to what we're actually doing and why we're doing as we do. In case things aren't explained properly, feel free to ask questions or do comments. I think we could do an actual recap episode whenever we get to a state where we actually done drawing, maybe drawing in 3D. I still find that the overall goal with this tutorial series is to render a 3D object to the screen, since we would have to implement both a depth buffer and a pipeline that is yeah, totally sufficient in terms of doing basic rendering. So yeah, but things of course have to make sense, and if you feel like they do not make sense, it's important to me that we go through the different areas that don't. Yeah. Um, yeah. Okay, I'm almost done with the coffee here. So in a couple of minutes I'll start the next episode. If you're watching this in the future, remember that the GitHub repo allows you to download um, different versions of the source code. So you can always grab the latest, but you can also grab earlier commits if you want to uh, do some changes or experiment with another way of setting up your project. Yeah. Okay. Remember to cast votes on the different polls on the channel. I think when we're done with this series here, I'll make a poll in terms of whether we should expand the tutorial series a bit. Um, yeah, as I've mentioned in the previous episode, there need to be a certain level of support in terms of doing these episodes, since yeah, I'm only doing this part-time, and I also would like to do streams on our or rather my game project itself. So yeah, there needs to be some balance in terms of interest. and need for discussion of different topics or different tutorial videos um, before I will allocate time to do them. Yeah. Okay. Um, let's see. Okay, am I about to be ready here? Yeah, I probably think so. Let me see. Okay. Maybe we should just get into it. Yeah, I'm a bit tired, so I might be a bit more slow today than usual. Uh, yeah. Um, okay, let me just swap this and set up stuff here. Okay, I'll start the recording. Hello and welcome to our next episode in the DirectX tutorial series where we create a DirectX 12 application in C++ from scratch. This is rather as always, a part of a live stream where I do separate recordings on the different topics that we go through throughout the process. And since it's a live stream, primarily featured on YouTube, I will be doing questions, preferably at the end of each video. If you're watching this in the future and you have questions in terms of why something is the way that it is, feel free to leave a comment. I'll do replies as well as I can. Yeah, the GitHub repo gets updated between every video segment that you will find on the actual channel itself. So you can always go back to a previous episode by using the different commit history points or whatever you call them, different commits, earlier commits. I hope that everything is explained in a meaningful way and that these steps so far have made sense. If not, feel free to let me know and I could do a recap episode or a elaboration on different topics. If there are a lot of questions in the comments, I also will maybe do a um, combined episode where I answer your questions. Okay. So during our last episode, we set up our pipeline and our root signature. And during the pre-stream for this episode, I outlined some next steps in terms of what we need to do. We want to bind the root signature and pipeline to the GPU/draw process. And we want to bind a data storage to the input assembler and give it a view/description. Remember, this is our pipeline. So the pipeline takes vertex buffers and sometimes index buffers as input and does rendering on them according to our shader programs. And it sometimes takes other input as um, parts of the root signature. So we need to bind that part of the input assembler stage, and then we need to tell the GPU how to interpret our data. Since we can interpret vertices in different ways. And then we want to do a draw call. Right now we have no 3D perspective, so I expect the draw call to be 2D. Okay. Let's see. I'll just make sure that I haven't missed something. Okay, I have actually missed something because we would like the output merger here to have a specific render target as well, so we actually also need to bind that. So let's go through the whole process here. Let's see. We also need to slot that in somewhere. Maybe we actually want to do it before we actually set any GPU pipeline state, because no matter what, we are expecting to use this specific output merger here. So we want to bind the render target to every part of our output merger. You could, of course, render to a texture instead of the render target. Yeah. So we clear our render target here. Let's start by setting our render target. We will do a command list GFX command. For that, we will set the output merger set render targets. And as you can see, we will specify a number of render target descriptors. We also need to give it the address. Well, our address is just above us. We already defined the address/handle of our render target, and we do not pass in a handle to a descriptor range, since there's only one descriptor here, and we do not provide a depth stencil descriptor right now. So we slot that in, and we will do our draw calls here because down here we transition out of the render target state. So we need to do that here. So that's the first step. Check. Then we want to bind the root signature. Let's see. We want to ask our command list here as a graphics command. Bind maybe set root signature. Set graphics root signature. Yeah, we have a call for that. Okay, we need to provide a pointer to the underlying interface of our root signature. Since it's stored on the pipeline state object here, we should create a method where we can get a pointer to the interface, and we will do an inline function here, get root signature, where we return the root signature pointer to the underlying interface. So inside our renderer here, we can do our root signature base pipeline state get root signature address, and we simply bind that. Then we also want to bind our pipeline as mentioned in the outline here. Set, let's see, do we have something? Set pipeline state. Okay, there we go. So our base pipeline, since it's a COM pointer that wraps the underlying interface, we can simply just call get on the class itself, and we will bind our pipeline. All right, things are going smoothly so far. Then we need to bind a view. Let's just swap these since we could easily get done with this part of the setup. We want to register a command, and IntelliSense already knew what we wanted to do. We want to set the primitive type topology. And let's see, the 3D primitive topology. I think we will do a triangle list if I recall correctly. Let me just be certain. Yeah, we will do a triangle list. So now the pipeline expects vertices to be grouped in 3 and to be the basis of yeah, triangulated faces. All right. Well, last step is to create a, not last step, but the next step is to create a so-called vertex buffer view, since we need to bind that to the input assembler. We have a resource that we want to be a dynamic vertex buffer. So therefore, we can simply create a vertex buffer view for that. Let's see. Let's arrange ourselves so that we do everything related to the buffer in one place. T3D12 vertex buffer view is the data storage for this. Maybe we want our renderer API to store that for us so that we do not need to create it all the time. Dynamic vertex buffer view. And we want to specify the buffer location. It's a virtual address, the size of in bytes, and the stride in bytes, meaning how is the buffer itself actually laid out in memory. So let's fill out the description here. Our buffer location is, of course, our buffer location here is, of course, our GPU virtual address, as you can see here. So we need to fetch that vertex buffer here. And maybe if we get the underlying interface, we could get the GPU virtual address. Okay. Then we want to set the overall stride in bytes, meaning how should the buffer be interpreted in terms of, if you look at the buffer, how are the different elements stored? How many bytes does it span per instance or element? And here we want to tell it, that we have a vertex layout, which are our structure here that actually gets stored in our buffer. And then we need to tell it the total size in bytes, so it knows where the buffer ends. And since we created a buffer with 16 kilobytes here, we will simply store that. So it's basically some of the same components here that is used to describe the buffer itself for the pipeline. In my other project, I do it on the actual resource itself, so that the renderer doesn't have to store it, but the object, the resource itself, can provide its own description. But yeah, it's fairly simple to implement, and you can do it as you see fit. We just need to provide a so-called view/description of the object, and we do that now. Last thing is that we want to bind the actual description here. So we do another graphics command list call where we set the input assembler, set vertex buffers, and we simply bind it. I think we will, let me just look up the actual input slot itself. I think it's 0, yeah. So the first slot here, the number of views that we provide, and a reference to the actual buffer view. Let's see, dynamic buffer view, and the address of that. Now it knows that this is not an array, this is just one single instance of a vertex buffer. All right. That should be it. Let's see if everything compiles and if we can actually do a draw call. Okay, we have some error. Okay, so it complains that we haven't done a specific. Okay, we have a problem creating the pipeline state here. Okay, let's look into that. Okay, if we the vertex shader expects application provided input data. But none is bound. Okay. Let's see. Let's look up this error. Well, we're not getting any help from our search here. Okay, I think this relates to probably our pipeline description. So maybe we're not done in terms of doing the description itself. Oh, wait a minute. Oh, wait a minute. There's an error in the old code, I think. We simply do this description here, but we do not bind it to our pipeline. So we just created the data here, but we need to pass it into our description, which our debugger here kindly tells us. So we need to set an input layout with as our input layout here and copy it over. Let's see. Let's set that as a grouping here. And there we go. No errors, no problems. We still need to release some resources. We will handle that later. Yeah, so during our last episode, I forgot that part. Yeah, but since we're not doing any drawing in terms of that, I don't think you'd run into problems. But maybe I should specify a note on last and the episode with the pipeline needs input assembler set. Okay, that is a note for my future self to remember. Okay, but other than that, we actually succeeded in binding our information here. But right now we only upload one vertex, and right now we have no way of interpreting our information, since our or rather we do, but our shader programs here get important, because let's see what we do with the actual input. Well, in the vertex shader, we simply pass it along as a SV position, meaning that this is a specification of where the pixel object is located in screen space. So we simply take our 3D space position and add an extra element, since that's needed for this position here. Yeah, and we pass along the color. So we basically pass the information along, and then for each position, pixel position, the pixel shader just draws the color. The point I'm trying to get to is that since we have no real computation between what is 3D space and 2D space, this position here actually describes a 2D screen space position, because the vertex shader simply passes it along. That means that the actual positions are in screen space coordinates, and let's see screen space coordinates of DirectX. And as you can see here, the screen space coordinates are as follows in DirectX. So they are mapped on the x axis as -1 to 1, and on the y axis 1 to -1. So let's add that to our layout here. Right now for screen space coordinates, vertices only have x and y mapped to -1.1 to 1 -1, right? Yeah. So we need to be mindful of that since we're doing 2D rendering right now. So let's say that we wanted a color here for the first vertex. Let's do 0. Maybe we, to help ourselves do this more easily, we actually want to store them in a vector and pass along the pointer to the underlying data. So let's see, let's do this instead. We create 3 vertices, enough to do a triangle. Like this. We will create a vector that will hold our 3 vertices, since that will be easier. So maybe we want to give them different colors. Right now, maybe we want to do only red here. And we will do some basic if statements. It's not great code, but we're not really trying to build a piece of software that is elegant, since you would need better structure overall to do more elaborate things. Right now we're just trying to test out our draw course here. So if the index is 0, we do something else. If it's 1, we do something, and then lastly we do something if it's not any of those. Where? Oops. Okay. So we need to remember our coordinates here. Okay. Maybe we want to draw the first vertex at our lower left corner. So that would mean that we need the coordinates of -1, -1. So our first vertex here will do -1, -1, and this will just be 0 because we are not using it. Okay, maybe since we're doing, if you can remember, the winding order is clockwise. So therefore, if we draw our next vertex up here, we would need something like 0 dot 1. So the x is 0 and the y is 1. Then we want to do our last vertex down here, which means it will have the position of 1 and -1. And that's it for our vertices. We of course need to add them to our vertex data struct here, or rather a list of vertices. And now we want to do the memory copying of the data. So we do a mem copy to the destination, but we take our vertices data storage and actually get the underlying pointer, and then we need to do a size of our vertex data structure times the size of the vertices here, because we want to copy the whole buffer. All right. Let's see if our upload of the data actually got done correctly. So we will use Insight, since I think that the layout is a bit prettier inside of this debugger here. Okay. If you run into trouble with the debugger, I'll show you why. It's typically because the debugger references the program that is in here, but it suddenly can't find the shaders, because whenever we do the running from the Visual Studio environment, everything gets mapped to this folder here, since it's our opening application and it knows where these files are located. So whenever we just open our program, as we would do usually, you can see that it doesn't know where to find the shaders. So therefore, we need to provide the shaders, and now everything runs as expected. So let's try launching our debugger now. Everything looks great. We will capture a frame by pressing F11, and we will look into our buffers here. We have our dynamic vertex buffer, and we know that the layout of it is a series of 3 floats and then a series of 4 floats. Okay, you can see here our vertices got uploaded correctly, which is great. That means that now we can access them on the GPU. Let's try closing some of this. And that means that we should be able to register a draw call referencing this buffer that is now bound to the pipeline because of the view. It knows where to look, and it, as we saw, we know that there are 3 vertices in that particular buffer. Then we want to do a draw call. And we do not have an index buffer, so we will simply do an instance draw without indexing. Let's see how many vertices per instance. Well, we specified 3 vertices per instance. We specified an instance count that is, or rather, we only have 1. We start at 0, and we start at 0 for both the vertices and the instances in terms of their buffer location. And that's our draw call. Let's see what happens. Okay, nothing happens. Let's see. Maybe we want to change the clear color here. Maybe we're in trouble in terms of actually drawing anything. Well, nothing happens still. We need to debug this. Let's see, we did not get any error codes. Okay. We need to debug this, figure out if we have been missing something. Okay, this is where our debugger tools come in handy, because we can now simply capture the frame, and we can look at what's happening. Okay, we have a event list over here where we do an instance draw call. It also gets an object here. Let's see. Whoops. It gets an event here So we can open the event, we can open the geometry, and we actually do get some kind of geometry that is supposed to be rendered. So maybe the problem is not that we have trouble creating correct draw calls. Everything seems to be all right in that regard. So maybe if we debug the locations here, maybe we're not doing the correct screen spacing coordinates. Well, first we have the -1.1. We have then our second vertex, which we specify, let's see, -1.1. That's actually up here, right? Yeah, we wanted minus minus, right? Yeah. So maybe our vertex didn't get specified correctly. Maybe we actually made a mistake right there in terms of figuring out where to draw it on the screen. So let's check the first vertex. DirectX screen space coordinates. Let's see. Let's look up the image again here. So we want. Let me just open this window here, or rather the image here. Okay. So actually, I wanted to draw the vertex down here, so we need to specify -1, -1, and then up here is the second vertex. So that is correct, since 0 is the midpoint on the x-axis, and the y-axis is specified as 1 up here. Then our last vertex is down here, and that should be 1 -1. That also explains why our geometry, when we actually inspected the draw call in the debugger, looked weird. Okay, we still do not see anything on the screen. Let's look up our geometry on the actual debugger. I expect that the geometry is fine, but we might have a problem in terms of our actual, what do you call it, shader programs. Okay, let's look up the geometry. We have a nicely shaped triangle, so that's not the problem. The geometry does get created correctly during our draw call. So what's going on? Maybe our winding order is wrong. Maybe our calling is wrong. Maybe our shader program is wrong some way. So we need to debug this, because we can see that our geometry gets created correctly. Our data gets uploaded correctly. Everything should be fine, but we're not seeing anything on the screen. So let's try doing no culling here. All right. And did we, let's inspect our color for the rendered primitive. We specified a green color. So that's not it. Okay. Let's try swapping the winding order here. Even though since we're not doing any culling, this should not be the issue. Let's try disabling the clipping here. All right. It's none of these issues. So I suspect that it's related to our shader programs. Right now we pass along this information here. Let me just see. I have a 2D shader in my other project. So I'll just look up what we do there. Yeah, you only specify the less components, and we have specified zeros. So that should be fine. Let's look at the, let me just look at the pixel shader here. Um, mm, so that should also be fine, at least for a 2D renderer. So this probably relates to something in terms of our pipeline state. Let's see, we copy the position itself, we copy the color, and we do specify the clip space. Okay, let's do some more debugging in NVIDIA Insight here. We capture a frame. So let's see, let's inspect our buffers here. We have a second revision, meaning that something happens to the actual thing here, but nothing gets rendered to it. So we definitely do have a draw call, but there's no output, and it's probably related to our pipeline. Let's see, let's close this. This is the scrubber. Let's inspect this. Yeah, you can see everything is expected to be green. Let's see our pipeline state here. The oh well, that looks a bit weird, doesn't it? Let's see if we have any linked shader programs. Well, it does recognize our shader programs here. So it should be all right, even though, oh, whoops, now I accidentally closed it. But let's see, do we have any problems with this? No, it should be fine. It should be fine. We initialize. Okay, let me just look up the pipeline. here. We set up the blobs themselves, and they are stored correctly. We have solid. We have let's try. Maybe we need to specify a depth stencil even though we're not using one. Let's see. We have a sample mask. That looks fine. Wait a minute. This actually needs an extra F. An extra F for fail. Let's see. Let's see. Maybe we need a blend state, render target, right mask, color, right, enable all. Let's try that. We still do not see anything on our screen here. We will continue debugging. Maybe we don't want to reset this to 0 because we might end up specifying something that we do not want. Maybe we want this to be the default. Well, did we create? Yeah, I guess we create the zeroed out one. Let's see if we. Okay. Let's see. So that actually crashes our program. I think we are fine at setting everything to 0 here. I don't think we need to do that when we actually do it. Okay. We disable the blend state. We set the render target right mask. Oh, yeah. And let's make sure that excuse me. Yeah, that the depth enable is false. Okay. We still see nothing. And let's try enabling this again. Nope, it's not pertaining to that. So we do get both elements. Is it our calls? I mean, the draw call itself should be fine. Okay, maybe I'll debug a bit in terms of no, let me just show the whole process, because let's figure it out together. I can't remember why it doesn't register that. Let's see. Maybe I need to do we do set the output merger. And the draw call itself actually results in the whole thing trying to draw the triangle, because the back buffer gets updated. And we saw that the percent function should flip the back buffer itself. Yeah, it increases the buffer count and wraps it. Let's see, can we the pixel shader here? Let's see, do we have a problem with our, well, if we change this to debug mode, we can always run the program here with different shaders. Let's do just a float for where we create a color that is all white, and then we disable this. Well, no. So let's see. Undefined. The output merger here takes our texture. So nothing gets passed to our output merger here. I can't remember what the problem is. I've done this before, but It's been a while since I started over. Instance count 1. True, did we set that to true? No. Solid call none. Uh, mm, mm. Yeah, okay. I think I'll end the recording here and do some debugging. I'll show you the solution in the next video series. Yeah, it's been far too long since I started over, so it's hard for me to recall what the actual problem is. We probably have to set some state. In terms of, yeah, we try to change the color to just print out white for every vertex, but that didn't help. Yeah, I'll try to debug it. I'll be yeah, showing the solution in the future episode. All right, catch you in the next one. And on stream here, we will do some more debugging. I mean, the geometry is pretty clear. Uh, let's look up this parameter. Okay, let's try changing our C component here. Maybe we want a 1. Nope, that's not it. instead back. Let's see. And this. Mm, can we do triangle? No, we do triangle lists here. It doesn't matter. Start slot, number of views. That's fine. Vertex count per instance. That's also fine. What if we swap the ordering? Yeah, nothing happens here. Let's see. Oh, why did I forget what the problem is? So the depth state set to that. Let's see. The geometry is input like that, so that's fine. Our input is fine. It's our position. It's our color. So semantic name. Default color mode is none. Front counterclockwise. I'm not sure it's supposed to do that, but and then the pixel shader here. Input primitive. Oh, that's related to the geometry shader. Let's see. Depth 0. Oh, I can't remember the fix. I can't remember the fix. Why does it actually show more resources? Well, not that. Event details. Object browser. I don't know why it. Uh, mm, Sampling description, node mask. Uh, Bytecode length 1. Uh, uh. Let me just compare to another project. Let me see. New project, temp. Let's see. Try opening. This will probably not work, but let's see. No, it still stalls here. Okay. Cancel and terminate. Okay. We want to do a different project. I think I have one that is old. Let's see. Let's try this one. Now. Well, nothing appears on the screen here. Let me see. Did it have any debugging issue? No. Uh, mm, yeah, I'll just disable the screen since I have some projects that shouldn't be streamed. So let me see. Let me just swap to this and do this program instead. I think yeah, that one is fine. So let's check out the pipeline state here. Object browser, pipeline state, polygon, root signature. Let's see, it still says the same thing. The sample mask. False, false, false. Let's try enabling the depth stencil stuff. Yeah, because I think that's the only difference. Maybe we need to bind a depth buffer for that, but yeah, let's try doing that. That's the only potential problem that I see with the pipeline state itself. Let's try doing true here, and then we probably have to depth func less depth right mask right all. Let's see. Well, it didn't change anything in terms of that. Let's see, do we have any problems? Yeah, warning. Okay, as long as we don't intend to bind something, it's fine. Oh, what's the problem here? I can't remember. I simply can't remember. Is it related to our pixel shader here? Let me see. What kind of shader programs do we? Let me just copy the sample mask here. Oops. Yeah, it's the same. Let's just mess a bit around with some of these vertices here. Maybe we want to have that and have that, have that and have that. And then I can't remember the fix. What did I do back in the day? Because my other pipeline is actually fine in terms of doing the 2D rendering. And we're not recording in the wrong order, right? Let's see. Let's do 2 instances here. Well, one instance is fine. And let's see our shader compilation here. All resources bound. Let's try disabling that. Doesn't change anything. Let's try flipping the winding order so this gets specified last. Well, nope, that's not it. I know the problem whenever I remember it. Let me look up. Uh, well, let me see. Let's look up some resources here. Let's see how they do it. If in terms of if I miss something, rendering. Let's see. They do a whole 3D project. Let's do Brian's soft here instead because initializing this web page is really slow. I'm certain I just missed something. It does know how to interpret it. Drawing. Let me just try disabling the root signature for now. Let's do store the old component here and then this should be fine. doesn't change anything, so that's not it. It's not because we expect a thing to be bound to the Oh, now, hello. No problem, man. Welcome to the stream. I'm just hanging out right now. I think I know what's going on. I haven't defined a viewport. I just realized that we're doing everything right. Oh, okay. I totally forgot to define a viewport. Let's try it out. Doing that. Oh my god, maybe that's the whole problem. How can I forget the viewport? Okay. Let me just test out that. Window background color, what do you mean? Yeah, I did that in a previous episode, but we're not using it for anything yet. Right now I'm debugging, so feel free to ask questions or do recaps. I'll continue the recording in a bit. But let me just do something here. I'll of course redo it when I start the recording again if it ends up solving our problem. Let's do a rect client rect because I think get client rect to our handle, and we set the we need a viewport on the 3D12 viewport, right? Or is it the 3D viewport? Yeah, I think it's like that. Viewport. Let's start out with that. Create the viewport here. Viewport. Width. Width. Viewport. Min depth. Viewport. Max depth. And we of course need to bind that. Let's try doing that after we do the clear color and set render target. Let's do this. Hopefully this is what I missed. I can't I really don't know why I didn't set the viewport. Let's see, this is probably not enough. We need to set a scissor rect as well. The 3D rect. 12 rect, yeah. Yes, rect. And we set it to let's see down here. We set up the information. left 0 right equals to our viewport the width, and our top is going to be 0. The edge rect is going to be the bottom here, viewport right. Uh, Yeah, I was wondering why everything was set up correctly, but nothing showed on the screen, and I realized that I might need to set up both a sysrect and a viewport to get anything actually to be displayed on our screen. Yeah, I just wanted to test that out since I spent a lot of time trying to debug the whole thing. And there we go. That's the problem. I forgot that. Okay, I need to do this in an episode then. Let's see. Let's just comment this out. Yeah. I knew I was doing everything correct, but I forgot to implement the sysrect. Okay. Yeah. Yeah, I think so. But let me just do. Yeah, I will make 3D next. We will do it here on the stream. Um, but let me just do a recording. And I'll clip it together since I spent a lot of different time doing the debug. Yeah, we have some different math stuff to do in terms of that. So let me just see. Let me just add this here. All right. Let me see, can I actually do editing on YouTube in terms of combining videos? Mm, mm. Oh, maybe I need to do it manually, but my video editing software only supports 720p, which is a problem because I don't find the resolution sufficient to actually see the code. Okay, I think I need to upload the previous video here. Let's see. Yeah, so any viewers on the stream here, I'll just do a short break where I edit the, or maybe, no, maybe I'm not supposed to do that. Maybe I just upload the episode and, no, I can't really figure out how to do it properly. Let me see, how quick will YouTube let me edit anything if I upload it right away? No, I won't do editing. It's just that I spent approximately 20 minutes during the last recording trying to figure out what I had forgotten in terms of getting anything rendered to the screen. As you can see here, um, during the last episode, I only had a black screen, um, and I used NVIDIA Insight here to actually check whether everything was in order. And um, when I did the debugging here, I could see that our draw call got registered correctly, and the input assembler even had the correct geometry. So I knew that the data was correctly uploaded to the GPU, and the draw call itself was fine. And I looked through all the shader programs, and um, I also knew that they were correct. I then tried to figure out whether my vertices were incorrect, but they were also correct. So I couldn't remember why I couldn't get anything to draw on the screen. I was even looking through um, the um, the root signature here, rather the pipeline description, and I couldn't simply figure it out until I realized, wait a minute, I need to set the viewport and the sysorect to be able to show whatever I'm drawing. Right now, the screen hasn't been defined even, so yeah, it doesn't know, even though I have the correct screen space coordinates, where to draw to and which format to really interpret the whole thing. I um, I added um, in the episode about the root signature, I added a input slot for a future constant buffer, but I'm not using it right now. But I did a whole episode where I described the pipeline in terms of rendering, where I went through what does a root signature mean, and how do you bind something like constant buffers to the generalized pipeline. So yeah, I added support for a single root parameter in terms of a constant buffer, um, but we're not using it for anything. We will use it when we do 3D drawing. No, I won't be using the toolkit because, yeah, I don't even know the toolkit that well, so I've never used it. So I prefer to do everything myself. And this tutorial series is in terms of getting started with DirectX. I'll probably mention the toolkit library in the end of. Um, I know the I know the toolkit. Um, I had a viewer early on in the process that had to do a project with the DirectX toolkit, so I tried helping him out in terms of using the toolkit. But yeah, I don't think implementing everything from scratch here, as we do in this tutorial series, makes any sense in terms of using the toolkit. Then maybe for texture loading, I don't know. In the next video, I'll just try to, let me see. Yeah, the old video is processing. So I'll do an addendum to the previous video. Since we need to. No, I'll show how to add the viewport and scissor rect, and then we will decide on what to do. Since I promised that we would do draw calls during the last episode here, and we didn't get actually done with it, so I'll create the next section of that tutorial series so that anyone following along can actually see the end result on the screen. So let me just do the recording real quick, and then we will end that and decide on what to do next. Okay, yeah, well, we can discuss that. Let me do the video, and then we can discuss some general topics and maybe make a video of that. But I just want to complete the last episode, and then I'll be deciding on what to do next, and maybe discuss the topics that you've raised. Okay. Let me start the recording now. All right. Hi there. This is future me that have some knowledge about what I kinda forgot to show you how to implement in the last part of the video. It's not only enough to actually do these things. We have done our draw call, and everything should be fine. We have actually done this also, but I forgot that I forgot that not only do we have to make draw calls, we also have to define the actual screen in DirectX. And we do that by defining a so-called viewport, which is, yeah, a viewport. It's a definition on how big the screen is in pixels, where it's located, and so forth. And then we do something like something that is called a scissor rect, which is actually like using a cutting tool to cut out a piece of the screen that we actually want to render to. Since we will be wanting to show our entire screen, we of course define the scissor rect as the same as our entire screen. So this means that our renderer API needs to store two components. It needs to store a D3D viewport here, and it also needs to store a D3D12 scissor rect, which is just a rect, meaning a square defined by some bounds. Not only do we need to initialize them during our initialization step here, we also need to bind them to our draw call. You can do different scissor rects and different viewports, but yeah, we will define the top left X and Y position. Then we will define the viewport width and height, which will just be our entire rendering screen space. So since we store our width and height in our member variables, we just use those values. But we also need to store something about our minimum and maximum depth. And we will simply map that to our depth buffer range in DirectX. We do depth between 0 and 1 in Vulkan and OpenGL. There are different ways of defining the depth. I even think they are inverted from DirectX 12, or rather just DirectX in general. Then we define our sysrect, meaning how much of the viewport we actually want to cut out and do rendering to. And we will simply specify our whole viewport. And we will do the last part of it here. Height. There we go. Okay, now we've initialized our viewport and sysrect. We need to bind it. Usually you do that after the output merger binding. So we do it by using the graphics command list, and we call a command to set the viewport. So we have one viewport, and we have our viewport defined here, but we would need to provide the address of the struct. We also bind our sysrect and also give it the address of the struct. And we should be able to now do drawings to our entire screen. So let's see, does everything work? Everything works. I did some debugging trying to remember whatever might be wrong. So let me just show you the current pipeline state. I might have changed values. I probably haven't. I just did some debugging and wrote out the depth states a little more clearly, but it's basically the same as previous episodes. I did change the call mode to none so that we don't care about front face or front or back calling right now. But that's probably the only changes. The shaders didn't change themselves. So yeah, we now have our first triangle. Everything is great. So this is simply the video about doing draw calls. I think we're done with this video, and we will be discussing what to do next. I will do this on the live stream. So I will of course do an introduction in terms of what we're planning to do. I've promised that I will be going into 3D drawing, so we will probably take steps to do 3D drawing. Yeah, we could animate the triangle and so forth, but I'm not sure that's that is that interesting. So yeah, maybe we will just try to focus on getting 3D rendering going. But yeah, that's it for this episode. Thanks for tuning in. Feel free to comment, like, or subscribe. I'll make sure that the GitHub repo is updated in terms of this code that you see that is able to actually render a triangle. All right, take care. See you in the next one. Bye bye. Okay, and I've stopped the recording now. So let me just fix the upload of that part, and well, YouTube won't let me edit it yet. So yeah, I'll probably split it up into two. Let's see. Yeah, exactly. Yeah, and I'll cut out the debugging stuff in the video that went on too long while I couldn't figure out what I had forgotten. So yeah, so I'll probably split episode 15 into two parts. But YouTube needs to process it in terms of me doing editing. If I use my own editing software to combine the clips, I'll get a too low resolution, and I don't want that. Um, I probably also need to update the repo here. Let's see. Let me just fix this. Maybe I need some more coffee as well and a bathroom break. So it does allow me to do editing right now, or what? Yeah, I think I did spend approximately 25 minutes in the first part. No, there probably aren't that many on here on YouTube. Usually it's on the internet instead, or rather blogs instead. There are some, but yeah, I don't know. Okay, let me just do the commit here. I know the videos will be behind in terms of uh, the whole scheduling, but mm, well, at least I'm not a full-time YouTuber or anything like that. That's also why I won't be editing things. I don't really care about editing things. I find it a waste of my time, so I would rather do programming or projects. So hopefully things turn out okay without any editing, and yeah, people are able to use whatever content I provide, but it will just be as is. Now that would be somewhat of a surprise. I don't even think there's 1 million people interested in doing game development from scratch. Let's see, let's do a commit and then a synchronization here. Let me close all these tabs and simply open the render API. Did everything get pushed? Yeah, it did. Okay. Yeah. Yeah. Well, as I've mentioned, I'm only doing YouTubing as a hobby, so um, I'm not trying to develop a large channel. If people like the content, they like the content. If not, they don't, and it's perfectly fine. Um, I do mind about helping uh, new programmers out, so that means that I do like doing tutorial kind of stuff, but I'm not even a professional programmer, so um, people need to take my advice with a grain of salt. There's probably way more um, skilled people out there. I mean, so far I've managed to do quite all right with my own project. I think it's gotten pretty far. So I'm not so a total idiot in terms of doing tutorial content, but I'm certainly not a professional or expert in either way. Yeah. So if I am able to reach a point where I can maybe do, yeah, hopefully, but even if I have a few thousand subscribers and I can do a tiny bit of monetization, maybe I can um, uh, yeah, do a bit of yeah, I don't know, monetization in terms of maybe doing ads or doing something like that, and then I can support my own projects here in terms of maybe upgrading my GPU or getting a better microphone or doing something like that that will support not only the channel but game development itself. So, but if it never reaches that, haha, thank you, man. That's kind of you. I'm not certain that all of it will be worth your time, but thank you anyway. All right. Um, Let me just do a short bathroom break and another cup of coffee. I'm pretty tired today since I went out last night and got home pretty late. So, and then I can go through the question you had about how the GPU and CPU work together right now, uh, using the sample code here as an example, and then we can do maybe other questions slash topics, and then we will make the next video. I'll be right back. Let me see. Well, uh, I guess you could do that, but I'm working a full-time job and only do this as a hobby side project, so I will never find the time to do any editing. I mean, I literally think that it's a waste of my time since I have a job and I need to work full time on that job. And uh, I like making videos, but I don't like editing. I really don't care for it, and I would rather not do any videos and just do programming than I would do videos and editing. So that means that the content will just be unedited, and yeah, I really don't care about that. Maybe occasionally I do my monthly updates in an edited fashion, but that's not something that needs to be high resolution and uh, super crisp or anything like that. So yeah, it's not that much of a hassle to edit that, but I really don't care about it. And uh, yeah, exactly. And I would end up using my spare time um, editing more than I would do programming or anything else. So yeah, I do think that that would be a waste of my time. Um, yeah, and yeah, as I've said, I would rather simply not do video content than edit it. So I think this is the best compromise. I think I'm too old to do video streaming in terms of gameplay, but yeah. And I would also rather just program and do different kinds of stuff. So yeah, I just have to live with that. My audience will be narrow, and it's not certain that I will be able to monetize any of this, and it's fine. I have a job besides it, so um, it'll be all right. All right. Should we dive a bit into how the CPU and GPU actually work? Or let me see. Yeah, did you have any? Let's see. Okay. Yeah, I think that was the primary question you asked. So I can do that now if you want to before we decide on what to do in terms of the next video. Well, yeah. I don't think so. Maybe when the Factorio expansion gets released, I'll do a streaming series of that, since I almost played Factorio for 1,000 hours in total. So, but that's basically like programming anyway. So might as well just do a programming stream. Yeah, I don't know. Maybe we will. Yeah, I don't know. Since I'm probably gonna play it anyway, I could do that, but the other games I play, I probably won't be streaming since I do it with friends, and yeah, I'm pretty sure they don't like to be co-casted into a streaming series. But anyway, should we get going? I can drink my coffee while, as we go along. Okay, you're gonna go? Well, if you need to go, then also take care. Thanks for dropping by. Sure thing. You can do whatever you like in terms of that. Uh, I just, yeah, I'll save your questions for a future time when you have the time to dive into these things. I'll just do the recording of the next video then. But sure, take care and good luck with your project. As a summary to anyone watching, um, either now or in the future, we will be doing the next episode in terms of this tutorial series here. And yeah, during the last episode, we got set up in terms of drawing a triangle to our screen. The next thing we need to do is to figure out what to do. I promised that we would do some 3D rendering, which means that we need to kind of like set up a camera, set up a 3D space, and also something called a depth buffer. But the depth buffer we can do last. So our current setup here can be elaborated on in terms of um, what do you call it? Uh, Making a 3D output. So yeah, let me just try to plan out the next episode then. In order to do 3D rendering, we need to define a 3D space with 3 axes, we need to define the coordinate system axis in relation to each other. By that I mean, for example, which axis is up, which is forward, which is the right axis. As in meaning the direction right, not the proper direction. Anyway, in that coordinate space, we need to define a camera slash eye position with a looking direction, because our camera needs to be placed in this 3D coordinate system of things, and it needs to look somewhere. Preferably, it will look at whatever we want to draw. A easy way of doing things is to define a 3D object at the origin 0.0.0, and then offset the camera and set it to look at the origin. When you have defined your coordinate system, your camera, and even your 3D model or object or vertices, you can then start uploading them to your graphics pipeline and do shader computations on different stuff. In our last series here, we saw that we only take 2D screen space coordinates and pass them in as vertices, meaning that these vertices only have X and Y coordinates. They do not have a Z coordinate, which means they are not 3D. We specified up here that we're mapping directly into screen space. And our our vertex shader simply passes the input that we get from the input assembler further along the pipeline into the rasterization unit, of course, but after that into the pixel shader. And we simply change the input semantic called position into something called SV position, which is used in the pixel shader. And the SV position is in screen space coordinates. Screen space coordinates. So that means that whatever this position gets defined as, it's in screen space coordinates. So we could end up in a situation where we have a 3D coordinate space definition of each vertex's position, and we need somehow to convert that into a 2D space screen space coordinate system. And in graphics programming, that is handled by the view projection matrix. So it basically is a series of math computations that kind of translates this 3D view here into a 2D screen space. so that the system knows what pixels to draw. In terms of the math, I shouldn't dive into the math behind it because, yeah, this is more a series focused on the actual programming, but we need to at least address the math here. Math and the actual shader computations that translate from 3D world space into 2D clip space slash screen space. So we need to address that. Lastly, we will probably need an episode on the depth buffering, because in 3D rendering you need to handle depth. It's specified in terms of the 3D coordinate space, but once we translate into clip space, screen space, we need some way of defining how the pixels are supposed to be in relation to each other, which is closest to the screen and which ones are the furthest, so that you get a proper sense of depth. As you can see here in the camera viewing frustum, as it's called, things further behind near the far plane of the frustum shouldn't be drawn if there's an overlapping object closer to the near plane that obscures the object. So yeah, that's depth buffering, and it is handled by the shaders and the generalized 3D rendering pipeline. So yeah, I think these are the topics that we need to do in terms of getting set up. I think that we will do the first video. First video will be on math, not in detail, of course, but just the general principles uh, on coordinate systems. And some functionality that Microsoft has provided us with in the DirectX math library. To set up our 3D world. So that will be the first video. It will contain limited coding and be a bit of a more theoretical video. Then we will do, we could do a camera class. Well, yeah, I don't think we will do that because maybe you don't need a camera per se in your application. So I will refer to something like a camera, but yeah, we will probably not implement it in detail. Okay. This means that we also need to, let's do it in the same video, need to discuss a bit about the view and the projection matrix. And then we would need to do a video about uploading the camera slash viewpoint matrix that helps translate from 3D space into 2D screen space. Again, using this model here, let's see, can we actually open it? Yeah, we can. We will use that. And we will be using a constant buffer. So we need to talk a bit about that. And we need to bind that to the pipeline. And then we could do a short video on rendering a 3D box and doing the depth buffering. And then we should hopefully have a working 3D application. Creating the vertices and uploading them. We'll already upload data, so it's not that hard. And then we need to discuss whether we need a video number 4. Since I think that we will be around the point where this series is will have arrived at the endpoint in terms of getting set up and actually rendering something using DirectX 12 and having the most basics working blocks of a graphics pipeline. Maybe we want to do one episode on uploading data to the default heap, since I think that probably is a work in progress that we left out in terms of doing the resource management. This will also contain a bit more about resource barriers, and then yeah, we're probably done in terms of doing basic stuff, and then I will need to consider what to do in terms of future projects. So yeah, I think that's the outline. Okay. Okay. I should probably just start the next episode then. I'll do editing of episode 15 later on when YouTube allows me to actually do some editing to it. Let's see. Well, yeah, right now it's not really responsive, so I think it needs some more time to be ready. All right, we will just do the recording here then. Okay, I'll start the recording. Hi, and welcome to the next video in the series of doing a tutorial for creating your first DirectX application in C++, completely from scratch. In in our last episode, we defined the viewport and the sysrect and created a 2D triangle rendered to our screen by specifying 3 vertices here that we stored on the GPU in terms of the upload heap, and we did a basic draw call. Since I've been advertising that we should do 3D drawing as the end goal of this tutorial series, I've laid an outline for the next potentially 4 videos, depending on how long we take, where we will do the stepping stones in terms of what is needed to be done to do 3D drawing. Right now, we have a pipeline where our shader programs process our vertices and they translate them directly into clip space / screen space, which means where they should be placed on the actual screen. And as you can see here, our vertices are defined in 2D space since they only have an X and a Y component. This means that this is not 3D. Even if we added a C component, it wouldn't really matter, because whenever the vertex shader here outputs a SV position, it is interpreted as in clip space, meaning screen space. So we might specify a 3D position, but the vertex shader can't really handle a 3D position. It doesn't know what to do with it. And it needs to pass along a 2D position to the rasterization unit and pixel shader. So that's a problem. We need some way of defining a translation method between 3D and 2D space. Also, when you work in 3D, you need to define not only your 3D a translation method between 3D and 2D, you also need to define the actual space. It has to have 3 axes, since it has 3 dimensions, obviously, and you need to define which axis is up, which is forward, which is right. And there are different ways of defining such a coordinate system, and we will look into what DirectX usually does. So let's look up DirectX coordinate system. And let's see, we have an article here. DirectX uses a left-handed coordinate system. And if you're using a right-handed coordinate system, which might be if you're porting from OpenGL, they say that you need to flip the order of the triangle, and you also need to change a so-called view matrix. My own project, which I do here on the channel during live streams, actually uses a right-hand coordinate system, even though if we work in DirectX. But that's because I usually do Blender for modeling, and that uses OpenGL, and therefore we need to use a right-handed sided coordinate system. Otherwise, I had to do a lot of computations to the models and so forth, and I haven't done that yet. So, but in this series, we will be using the intended left-hand coordinate system. There are some functions here referenced that if you want to obtain a translation method for a right-handed coordinate system. DirectX Math provides utility functions for that. All right, but what am I actually talking about in terms of translation? Imagine that this box here contains a 3D coordinate system. As you can see inside the box, it has an up axis, it has a forward going axis, and a right going axis. It's defined entirely on all three axes. The box contains three components for each vertex. But we need to translate it into screen space so that we can see something rendered to our 2D screen. So you usually do that by defining a eye, a camera, call it whatever you want, but simply a viewpoint. And you define that viewpoint in 3D space in terms of how close to the lens of this viewpoint can you actually go, and how far out can you see. And that is actually a definition of a 3D space. So you need to warp it so you get a proper sense of depth, as you can see here. If you're trying to get a 2D perspective, which is the plane right here, for example, on a 3D object, you need to kind of like warp it so that it gets appropriately smaller or larger the further you are away from or closer to the camera. So you need some kind of translation into a so-called viewing frustum that then again needs to clip, or rather interpret how objects are visible in that scene. So let's see, maybe we can find another model. View projection, matrix, camera, frustum. Let's see. Yeah, I'm not sure I'm properly explaining it, but um, I hope it makes some sense. So we basically try to emulate this. We will have a 3D object, a near plane and a far plane on the camera, and we kind of need to translate this into some pixels that are mapped onto this plane here. So basically you're casting rays and deciding, well, there's an object here, but the rays that I've cast tells me that this object is blocking, so I won't be rendering that. But out here I can look besides this object and see something in the distance here, so I need to render that on my 2D plane. Let's see. Yeah, so it's basically a way of using clipping planes, a frustum, and 3D matrix computations to translate something from 3D coordinates into 2D screen space. Yeah, that is called the view and projection matrix, and usually you multiply those two matrices together so that you have a combined matrix that handles translations directly mathematically from 3D space with 3 coordinates into 2D space with only 2 coordinates. We will use DirectX Math to set up our matrices. Let me see, did I include it in here? Minimum, let's see, in the PCH, we did include DirectX Math. So DirectX Math has some different ways of defining different structures. Let's see. Yeah, we have different types, but we also have vectorized um, structures for intrinsics. We can store something called an XM matrix, which is basically an intrinsic version of a structure that holds 4 registers with 4 input points. Yeah, since we are doing matrix by matrix multiplication, we will do that. Let's just explore what the DirectX math library has to offer us in terms of coordinate systems. So let's just start defining a view matrix. A view matrix is a definition of how do we define the axis of our world. Which direction is right, which direction is up, which direction is forward, and do we have any specific offsetting or yeah, something like that. It's called translation in terms of math. So let's see, can we actually ask DirectX to get us a view matrix? Well, matrix. Okay, it probably start with matrix here. View. No. Orthographic perspective. Perspective might be the one that we're looking for. Let's look further down here. Okay, we will do a quick search. View matrix. Builds a view matrix for a left-handed coordinate system using a camera position and an up direction and a focal point. So if we define a position for a camera in 3D coordinates, a upgoing vector and a or rather a forward-going vector, something that we, or rather, let me rephrase that. If we define a focus point, that could be our origin, and a up direction, DirectX can DirectX Math can computate how our view matrix, which is the way that the camera coordinate system is set up, should be created. So I forgot to say that it's not actually the coordinate system of the world, but it's the coordinate system of the camera, because each vertex has to be transformed into the camera coordinate system so that we can do frustum calculations on the actual objects. It doesn't, if they are in 2 different coordinate systems, one is in world coordinate system, the coordinate system of the world, and one is in the coordinate system of the camera, these positions won't match, and you would get weird clippings in terms of when you try to use the so-called projection matrix to translate those vertices into 2D clip space. So you define the camera coordinate system, and you use that matrix to translate from world coordinate system into a camera coordinate system, and then you use those camera coordinate system coordinates, which are still 3D, to use a projection matrix to translate that into 2D. Hopefully that made sense. Anyway, we will use a matrix here. Let's see. Didn't we have a method or a data structure for that? Let's see. XM matrix. Okay. And let's call this our view matrix. We will set our view matrix to, yeah, let's just try using this method. We can use other methods, but this one is probably fine. I've used it before. And we need to look at left-handed. There we go. So we need to specify a vector in terms of where is our camera. Since we are using a left-handed coordinate system, we see that y is up, c is forward, positive c is forward, positive x is right. So let's say that our camera here is completely dead center on the x-axis, but it's maybe 1 unit up on the y-axis, and then it's 3 units translated backwards on the what do you call it, z-axis. And then since this is a XM vector, which is actually a register that contains 4 values, you need to specify the last component as a 0. Yeah, DirectX Math uses these vectors that are intrinsic related, which basically is a 128-bit register with a space for 4 floating point numbers. So it's actually like an array of 4 floating point numbers, even though we only use the first 3. So that's related to the type. Then we need to set the focus position, and we simply set that to our origin in world space coordinates. Remember, this is all in world space coordinates, and the method will do the computations in terms of figuring out how the camera coordinate system is supposed to be set up. So let's define our up direction in world space coordinates. So we remember that y is up. So we define a so-called unit vector, which has the length / magnitude of 1 as the up direction. And since it's an intrinsic, rather a register, we need to specify the 4th component, even though we don't care. All right. So now we actually have a view projection matrix, or rather view matrix. We also need the frustum matrix, which is actually a matrix here that builds a left-handed perspective projection matrix based on field of view. Let's just do that because we like field of view, and it's of course left-handed. We will do a DirectX XM matrix projection matrix, and we will set that up as a thing here by XM matrix perspective field of view, and we need to specify a angle for our field of view, and I think this is in radians. Let's see. Yeah. So how let's just do a quick calculator for people who um, are used to working in degrees. Online calculator. Enter degrees. Okay, we want a field of view of maybe 70 degrees. Okay, so that means we have a radian value of this. And then we want an aspect ratio. And let's do 16 divided by 9, a classic aspect ratio. We want to define our near plane in terms of distance, and then maybe a max viewing distance of 50. Why, thank you. And this is basically what we need to do in terms of creating a projection matrix. So let's review what we just created. We created a matrix that translates from world space coordinates into the camera's coordinate space. So that means that every vertex defined in a world space coordinate system can be multiplied by the view matrix to be translated into the camera's coordinate space. Then we have defined a projection matrix that takes anything in the camera coordinate space system and translates that into a 2D mapped position. In math, you can do several operations with matrices at once. You just need to multiply the matrices. So we will store on our rendering API a matrix that, let's see, yeah, I probably need to include the math library here. DirectX math. There we go. Where we call it view projection matrix. Yeah, it's a long name, I know, but I just want to be clear about what we're actually doing. And we will store that as our view matrix times our projection matrix. And this will do both translations to any vector slash vertex with 3D coordinates in world space coordinates into 2D space. So let's just use the debugger here to see what we actually end up with. In terms of math here, we do some computations, we do this. Let's see. Now we should have our view projection matrix, and sorry if you can't see it on the video. Maybe I could increase the size a bit here. Yeah, let me do that. Fonts and colors. Let's see the autos and increase the, okay. No, I have to redo it. Anyway, this matrix here contains some components. On the x-axis, it's supposed to do translations like that. Then on the y-axis, it's supposed to do like that, and yeah, so forth. So this basically contains our information. It contains some numbers. I can witness that, even though you might not be able to see it on the stream or the video. We could maybe just redo it. Let's see, just for good measure. Well, okay, it didn't register. Anyway, so that is basically it. What in terms of what we wanted to do for this video, we created a coordinate system. We created a translation between coordinate systems, since we have not only one coordinate system, but two. We have the world space coordinate system that is defined like this, with an origin at 0, 0. Then we have defined a camera that has its own coordinate system, and we have created a frustum that can be used to extrapolate vertices in camera space into 2D. So that's it. Hopefully my explanations weren't that confusing. If so, I'm sorry, but that's it for this part of the video. We didn't do a lot of coding here because, yeah, well, we needed to get the math sorted, otherwise it wouldn't make any sense what we were doing in the future. In the next episode, I'll show you how to actually upload this information to our GPU pipeline. And in the video after that, we will do the actual 3D rendering. All right. Thanks for tuning in. Feel free to comment, like, or subscribe if you found any of this helpful. Hopefully, I'll be seeing you in the next one. Bye-bye. Yeah, and here on the stream, I'll of course continue. I'll just upload the video so that YouTube can process it. So I can actually do it. I also have to do the GitHub repo here. So that will be episode 16, creating a view projection matrix. Let's commit that, save and commit, and do a push. No, I won't make it rotate in the next video. I will create a constant buffer and upload it to the GPU, but we won't be using it until video number 3. Let me see. Are there any questions before we move along, or? So far, not any. Doesn't seem like it. All right. Well, I'll do the next recording then. Okay, I'm starting the recording now. Hello and welcome to the next part of this tutorial series on how to make your first DirectX DirectX 12 application from scratch in C++. On at the last episode, we did some preparation in terms of being able to render in 3D. We created a so-called view projection matrix, and I went over how to define coordinate systems. Next, we will be uploading this information to the GPU so that we can actually use this in our vertex shader to translate any position that we receive as input into 2D coordinate space. So that's the plan for this episode. We also want to bind that structure to our pipeline. In terms of constant buffers, they are buffers that are readily accessible for the GPU pipeline. You can upload constant buffers into the upload heap if you plan to write to them often, or you can bind them or rather upload them to the default heap if you don't plan on changing them a lot. This will probably on several platforms be an optimization, but since we want to be able to control our camera each frame, we will be creating this constant buffer on our upload heap so that our CPU can write to it every frame, or even whenever it wants. But we preferably would like to only write to it once per frame. So we need a utility function because a constant buffer has a certain memory alignment. A constant buffer must always be aligned to 255 bytes, meaning that it needs to be multiples of 255 bytes, no matter how much data you store in it. We plan on storing a matrix, which is a 4x4 matrix, which means that it has 16 floating point numbers, 16 floating point numbers with 32 bits, meaning 4 bytes each, will be approximately 64 bytes if I'm not mistaken. So it's nowhere near the upper limit of the constant buffer, but we just have to live with that. The GPU architectures differ in terms of how efficient they are if the constant buffers aren't aligned to 255. So as a good practice on a broad of different platforms, it's wise to simply align stuff and experience a stable yeah, that everything is as performant as possible between across different platforms. So we need a little utility function here that we will create in a folder called utilities. We will create a CPP and header file for that. I'll use the class creation method, but I will actually delete the class, and then I'll define a namespace here, and inside that namespace I'll also define something called utils, and this will simply return an uint which it will be a method called calculate constant buffer alignment, and it will take in a const uint. Let's just do the same typing here. Allocation, and we will define it in our CPP file here. And we will simply return our allocation plus 255 bytes, ended with a bit shifted 255. So this will wrap our allocation into multiples of 255 bytes. It will always be 255 bytes at the minimum. So that's an utility function that we will use to define our buffer. In our rendering API here, we will create a D12 resource, constant buffer for our so-called pass data. We will call it pass data because it will be something that is needed for every rendering pass, potentially, since it's information about our camera, which is needed in so many different kinds of shaders. So we expected to upload it every frame, and we expect it to contain information about vital components or data needed by our shaders. We also need to define its contents. So we will have a data type that we will define inside our header file, and we will call this pass data, and we will use our DirectX XM matrix type here, and we will simply call it view projection matrix. Sometimes, oops, that's my other project identity. We can actually initialize it as an identity matrix, meaning qualifier. Huh. Let me look up this. I can't apparently. Let's see. Oh, I can. So yeah, we can initialize it as an identity matrix. If you don't know what that is, let me show you. An identity matrix is simply something that is defined like this, where the diagonal is 1 and everything else is 0. So in a 4x4 matrix, you can probably imagine how that looks. So we initialize that as that. We want our constant buffer to contain our pass data. So we created the data structure / resource here on the render API, but we want to initialize it, and we will give it our device. We will give it this size of the buffer, but remember it needs to be aligned to 255 bytes. So we will do an include up here, where we include our utilities. Utilities here. Excuse me. And we will ask our helper function here to calculate a aligned size of our pass data struct. So no matter how large we create how much we change that struct. We will get an align size. Then we want to create a specific heap, and we know when we create it on the upload heap that we need to specify both the upload heap and generic read as our initial resource state. And we simply pass in that information. And now we have initialized our buffer. Then you might recall that we can do this, but I think the time is ripe for us creating a little bit of change to our resource here. We want it to store a private pointer here that is its memory location, and we want a function here that returns its memory location, get memory. Let's do that. Let's create a function for that. And we can do if our memory is not set, we map the memory. And let's do a get here. And then on release, if we have a memory defined here, then we simply unmap it. So we simply call unmap. There we go. So now we can actually delete this, delete this, delete this. And then we can take our dynamic index buffer here, and we can get our CPU memory. And it will always map it if it's not mapped. And we can do the same thing here. But let's make sure everything compiles. Okay, we have a problem. Oh, wait a minute, we return a null pointer, of course. Well, there we go. Of course, we need to reset this afterwards, otherwise we can't unmap it. So now we should be fine. Oh well, let's see. We of course need to make sure that the interface is valid. Yeah, there we go. Okay. So now we can simply make sure that every time we want to memcopy something to our dynamic buffers on the upload heap, we simply ask for the CPU memory, and it will make sure that everything is mapped. And when we deallocate the object, it will of course make sure that that it gets unmapped. Okay, we would like our frame to start with an update of our actual past data, since it's required for the current iteration of the pipeline. So let's ask for our memory location here. Then let's take our view projection matrix, and then let's write our past data. Okay. Now we have uploaded the pass data to our GPU. Let's just test that everything turned out as it's supposed to in terms of the actual data ending up on, oh, we haven't updated the shaders, I think. It doesn't matter right now. We will do that later. Oh, wait a minute. We need to build in release mode. That's why. Because Insight runs on the release mode. There we go. Let's try doing it again. All right. That looks more reasonable. Let's try grabbing the information, and we have our buffer number 2. We haven't named it. We could do that, but yeah. And let's see if we define that this is supposed to be a float 4 times 4. We see that we have the first instance, which contains our view projection matrix. So everything got uploaded correctly. Okay. So now we have created our constant buffer, but we haven't bound it to our pipeline. On the CPU side, you want to bind it by simply linking it to the root signature. If you remember, our root signature here has a constant buffer view in its first parameter, and which is in the shader register 0 and the register space 0. It's available for the vertex buffer. So let me show you how to bind something like that. We need to bind it before we draw, because we will use it for draw calls. So it needs to be available. We will set a graphics root constant buffer view. That basically means that one of the root arguments will be set to a pointer to this specific constant buffer. Remember that it's index 0 since it's our first parameter, and then we need to specify the buffer location. And let's see if we ask for the pointer for the interface of the resource, we can ask for a GPU virtual address and simply pass that along. So this binds through the command list the constant buffer to the pipeline, and this should be fine. We have no errors here, even though it's happening every frame. So that means that the CPU side of things are actually done. We need to update our shader programs to access our buffer though. And I'll show you how to write the shader program for that. So since it's only available in our vertex shader, we will only define it here. We will create a constant buffer of a certain type. We need to define the type first. Let's call it pass data. And let's store a 4x4 float view projection. And let's interpret the constant buffer as our pass data here. And then we need to give it a name. Let's call it global pass data. And let's tell it which register it resides in. So it's B for constant buffers, and it's B0 since our root signature specified that it's in shader register 0. If we had register spaces, we would need to specify that. That could be something like, let me find the vertex shader here, something like T0 or something. Or I think S0. Yeah, I can, maybe so. Yeah, something like this. Yeah. space 0. But we do not use the spaces, so therefore we... Hello, man. Welcome. So now this means that our GPU actually has access to our constant buffer, since we have bound it through the root signature, we have bound it through the command list, and we have uploaded the data to the GPU, and therefore we can access it. Right now we won't do anything with it. We just needed to see that everything compiles. And that means we need to do the actual rendering and drawing in the next video. Since I think we got done with our outline for this video, let's see, we want to upload the camera viewpoint matrix, and that translates. We want to create a constant buffer and bind that to the pipeline. We have bound it through the CPU side with command list registrations, and we have bound it on the GPU side through the shader program. Also, the root signature helped us define where to bind the actual constant buffer to the whole pipeline. And that's it. Since we have planned that our third video will be actually rendering a 3D box. We will also go into depth buffering in the next episode. As you will see, we will run into depth problems if we do not. All right, that's it for this video here. Are there any questions related to this video here, or in general? Doesn't seem like it. All right, I'll end the recording, and I'll see you in the next one, where we will draw a 3D box draw screen. All right, thanks for watching. Feel free to comment, like, and subscribe. Follow on Twitch, or even support the channel. See you in the next one. As for the stream, we will continue onwards in just a moment. I will just upload the video here so YouTube can do its processing. And I'll of course update the repo as well. So this is, I did 16 before, right? Yeah, I did 16 before, now let's do 17. Creating and binding constant buffer, a constant buffer. Commit all, save. There we go. Are you leaving again? Oh, I guess he needed to go. All right. Well, I think I'll just continue. Yeah, okay. All right, all right. Are there any great algorithms in terms of doing unindexed buffered vertices? Videos, let's do all here. I usually do index buffering, but we're not using that right now, so we need to create more. I simply create an algorithm. Okay. Let's simply copy this then. The winding order is probably inverted for this one. Let me see. Does Frank Luna DirectX GitHub? There we go. Maybe he does have something common. Geometry generator. Mesh data, create box. Okay, let's just create it manually. I guess we could. Mm, we could change this. Whatever, I'm just gonna create them manually. Okay. Okay, I'll do that. Let me start the recording. Hello and welcome to the next part of this beginner's tutorial series on how to do your first DirectX 12 application in C++ from scratch. During the last episode, we uploaded and bound our newly created constant buffer to our graphics pipeline. The buffer contains the path data, which is basically a struct that holds our view projection matrix. We will use that to do 3D drawings. In this episode, we have planned to create a 3D box and upload it to the GPU. And then we will probably do some depth buffering. I may do that in a separate video, depending on how long this will take. So I've looked into different algorithms to create a box. Usually I use a index buffer, which reduces the amount of vertices needed in terms of drawing the box. Since we haven't implemented an index buffer yet, and we might not even in this episode, since it's fairly simple, you would simply create it like you would create a vertex buffer, and you would use that to do instance drawing, or rather index drawing, instead of iterating over every vertex. But yeah, maybe we will do that in the last video, implement a index buffer and upload every data point to our GPU. Since we would like to kind of like, yeah, well, um, clean up this code. Anyway, let us start out by defining what we're trying to do. We're trying to create a cube, 3D cube, that will have 6 faces that can be thought of sort of like this. And each face will consist of a triangle. So we need to define these faces and triangles by specifying their in total 6 vertices each. If you do instance buffering, or rather drawing, you can reduce the amount of vertices, then one face only takes 4 vertices. But we won't bother with that, and we will go through the rather long-winded approach of actually creating all the vertices without indexes. So let's start up by defining which planes these faces will be aligned to. We will do something that is axis aligned, so it's not rotated yet. We can always do that later on. Yeah. But let's look at our camera. Our camera is at the negative C position, a bit raised on the y-axis, and it's looking at the origin. So if we were to find the face that we are looking directly at, it's defined in the y and x plane. So let's start out by creating the y-x plane face. So we need something that is we need a triangle that is drawn from the low y position, and if we imagine our coordinate system here, sorry, going through down through here, we can imagine that this is a negative y value and a negative x value. It will also, in the 3D space on the C plane, actually be a negative value. So let's start out by defining our vertices here. We will simply do a vertex array here. Which will hold for now 16, but we will probably increase that. Let's set our first one to the negative x position of 1, the negative y position of 1, and the negative c position of 1. So this is the box plane. No, I don't think so. You can. But my connection is 320 megabits yeah, megabit per second. No, I won't show your OBS settings on the stream. I'm sorry, man. but I set the bitrate to 4,200 kilobits per second for full HD. I'll just type it in the chat. I don't know. No problem, man. Anyway, so we were defining our vertices here. So we want the face facing our camera, our face facing our camera here, to be defined by the 3 negative coordinates here. And then the next vertex will be this one, so it will be positive on the y, but otherwise it will be similar. Then we want to draw this one, since we're doing clockwise drawing. Let's see. That's the next vertex. So that will be positive on the x, negative on the y, and negative on the z. Then we will start drawing this one. We will start up here. Which will be basically the same as this one. It will have a positive y, but still a negative x and c. We will create the one with a positive y and sure thing, man. I'm just not really answering generalized stream questions because I'm recording a video for YouTube. So, and I can't help you debug your OBS problems. All right, so the next position is up here where the x is positive, the y is positive, and the c is negative. And then we do the last vertex, which is exactly the same as this one, where the x is positive, the y is negative, and the what do you call it? Yeah, you get the idea. All right, right now we have 6 vertices. We can keep it as is. Instead, we want to upload this data here. So we will give it a pointer to that array. We will right now upload 6 vertices. And our color is defined to be black. Let's do a default color of green, so that we don't need to specify it, but yeah, well, maybe we want to specify it. Let's see. This is the green color. Yeah, let's just do it in case we need debugging. Let's see. And the other part of the face here. Whoops. Let's swap that so that the ordering is all right. All right. Let's do this. It will probably look weird. Yeah. It actually doesn't show anything. That's because we have changed our underlying data structure. Let's see if it actually gets uploaded correctly though. And let's see, we want to sort it by these parameters. Well, we do have one. Let's do indices. We do have 6 vertices. All right. So right now we upload the vertices correctly. We do not draw them correctly since we right now only try to draw 3 vertices. Let's increase it to 6. It probably doesn't still show anything because the coordinates are now in world space coordinates. They are no longer mapped to screen space coordinates. So that means that we actually need to do some translations here. One quick note in terms of constant buffers and DirectX and DirectX math library. The matrices that are created with the DirectX math library are row major, and the shader language expects column major data ordering, which means that you have to flip your vector times matrix multiplications. It's just the way that the math library is built. I've done something else during my own project because there are a few optimizations of doing column major matrix ordering, but that might be a reason why you need to flip certain multiplications here. But the shader language has a method for multiplying uh, vertices/vectors with matrices. And remember, this is what needs to be ordered in a different order if you have column major ordering. Let's see. And this needs to be, of course, a float 4 where you add this 0, 1 because a 4x4 matrix can only be multiplied by a vector of 4 numbers. And since you don't want to discard the last matrix by vector multiplication, since it contains the so-called translation, you add a 1 to your position vector. All right, let's see if this changes anything. Right now you can see we actually have a primitive. So it worked. You might be asking, why does it look like that? Well, that is because of our camera position. So if we inside our, let's disable this code, we don't need it anymore. If, excuse me, we change our camera position not to be elevated, but looking directly at the face we just defined, we will see a square. So the higher we go, the more skewed the view on the plane will be. As you can see here, it's like we are looking at it from a different angle. Right now, there's no depth handling, so things might look weird. But we successfully defined this entire plane here. We could now do the next plane, which is going to be behind this. So let's define this 6, 7, 8, 9, and 10, 11 here. And we still have space, and we will double the amount of vertices. But we will change the color here so that this face is red instead. And we will, since we're doing the other plane, we should actually flip the ordering a bit, because we're basically drawing this one, which is on the other side. It will hold the positive C value for all vertices, and we should look into the ordering of them. Let's see, did I miss anyone? Nope. Okay, so since this point is actually the one that corresponds to this point here, but only with a positive C value, we can actually calculate that the first vertex is the one that we specified as the second one here. So let's flip those. It's the one that has a positive Y, a negative X, and now a positive C. So this is the first one. And let's move this. So our next vertex here will be the one that corresponds to this one. So it will have a negative X, a negative Y, and a positive C. So that simply fits. And then the last vertex will be this one, which actually corresponds to this one now. So it will have a positive Y, a positive X, and a positive C. All right, great stuff. Our next vertex here will be the one that corresponds to this one. So it will have a negative X, a negative Y, and a positive C. Then we will draw this one, which will be the one with the negative Y, the positive X, and the positive C. Then we will draw this one, which will be this one. So it will have a positive Y, a positive C, and a positive X. All right, let's try doing this, but we change the color. Right now we won't be seeing anything. And did we mess up anything here? Let's see. Oh yeah, we are actually not drawing the vertices themselves. That's why. And things might look really weird because we have no sense of depth right now. As you can see here, everything just gets overwritten. But we do have the sense of a plane that is actually extending backwards. All right, that's the two faces here. Yeah. Maybe we should do the two sides. Yeah, we could do that. Once we have made a practice in terms of doing these things, they well, they do get yeah, we generate them fairly quickly. But I actually think that the whole perspective thing is rather confusing. So even though we are generating vertices, the missing sense of depth means that things end up looking rather confusing. So we should probably set up the depth buffer here. Okay, a depth buffer is a buffer that controls uh, uh, how far into the 2D screen space things are supposed to be rendered, and it discards pixels that are obscured by other pixels, basically. So yeah, we will create the depth buffer. And it will actually be a different kind of buffer. So we need to do changes to our resources here. We would like to be able to initialize as depth buffer. We of course still need our device, but we want to be able to specify a width and a height. So let's create that method. We can reuse our heap properties. This will be created on the default heap. The GPU will be doing the writing to it. We will not be using the CPU to write to it, so we don't care that it's created out of reach for the CPU. We will create a texture, since the depth buffer is a texture that for each pixel gets filled with a depth value that tracks whether a future pixel is allowed to overwrite the current pixel. So we need to define the dimension, which is a texture 2D. And the alignment will be our standard alignment. I think it's a minimum of 16 kilobytes. And we will specify the width as our width, the height as our height, and since we do not have a 3D texture, we will only have an array size of 1. This will contain no MIP levels because we do not have scaled versions of the uh, depth stencil texture. The format will be simply double precision. Now we will store single values as a depth value. So let's see, DXGI format. Do we have something? Yeah. This is a type that is used for depth buffering. So D32 is actually an appropriate uh, format for this kind of buffer. We will initialize our sample this and we will not be using sampling, so we don't care. Then we need our resource layout, which is a texture that has an unknown type, and then we need to initialize with some flags. And flag allow depth stencil. Well, then we need to create our committed resource. Yeah, so we will do exactly as we did up here. We will create a committed resource. We will specify the heap properties. We will specify the resource description. And we will specify a resource state. And let's see, we have some depth right, I think. That sounds appropriate. We would like to write depth information to it at the standard, and then we, oh, did I specify something wrong here? Heap flex, okay, yeah, I missed that. The 3D heap flex none. And then, yeah, okay, and then the last component is a clear value. And it's a struct clear value that will be initialized as 0. And let's see, what does it contain? It contains some information about the depth stencil. It also contains a format. Remember, our format is specified right up here. Then we want some clear value information in terms of the depth stencil. Well, especially the depth. And the depth is a clear value of 1. Remember, DirectX scales depth values between 0 and 1. And I actually think that 0 is the one that is closest to the camera. If I do not recall incorrectly. Let's see, let's set the stencil to 0, meaning that we will not be doing any stenciling. And then we give it the, does it want the address? Yeah, it wants the address. And that's it, nothing else. And then we need to error creating depth buffer. Let's see, too few arguments in function call. We need heap properties, heap flex, the resource description, initial resource state. Oh, okay, we of course need to specify where to store it. We forgot the old IID PPV. All right. So now we actually can create a resource on our renderer API. We will store it up here since it's basically related to our pipeline. Depth buffer. And we will initialize it after we initialize our pipeline. Initialize as depth buffer. And we will pass in our device pointer. We will pass in our width and our height. And well, that creates our depth buffer. Since it's located on the GPU needs to know where to find it. We need a descriptor heap to contain the information about the depth buffer itself. We will create a small wrapper here inside a folder called the descriptors, and we will create a wrapper for that. descriptor heap. It will be really simple. But since our renderer API would like to store it, we will create one. Let's see, engine here. And of course, we want to include that here. And then we will create a wrapper, as per always, since this is a DirectX interface. Descriptor heap. And we will create an empty constructor that is defaulted. We will create a destructor. And we will create a release function. And we will, as per always, do the get and then reset here. We will do the release function on destruction. And we will allow our render API to store one of these. Let's see, we will move these since they are pipeline essentials. And we will include a descriptor heap. I actually think, oh, I didn't really name it correctly. Let's rename it to D12. And inside the class itself, D12. There we go. And of course, like this. All right. We will, of course, need some functionality. Let me just close some of this. Of course, we need to update that as well. Depth heap, disk heap, and we will need a initialize function. That will take a ID 3D12 device because it probably needs a device to initialize it. Let's see. Whoops. And we will simply try out, can we create a descriptor heap? Yeah, we can. What do we need? We need a descriptor heap description. And then we need somewhere to store it. So the 3D12 descriptor heap description, we will store that initialized as 0. And we will pass that in. And we will, of course, pass it our com pointer here. And we will wrap this in our YouTube eval h result. And error creating descriptor heap. Let's see, we missed a parenthesis here and want to create it like that, right? Did we miss one more? Yeah, we did. Okay. And let's see. Our descriptor heap here is supposed to contain a number of descriptors. Right now we will simply hard code maybe depth heap. Yeah, we will simply hard code it as a descriptor heap here. Okay, and the node mask is 0. And the flags are none. Does it need to be shader visible? I can't remember. I don't think so, but No, it doesn't need to be shared. It's output merger related, so I'm pretty sure that it doesn't need any flags. And lastly, we will set the type to a depth stencil heap. All right. And we will hard code it as a depth descriptor heap, initialize as a depth descriptor heap, and we will pass in our address of our um, um, device. Lastly, we need to actually create a description. So we will ask our device to create depth stencil view, and it needs a resource interface, which is our depth buffer here. Then it needs a depth stencil view description, d3d12 depth stencil view description, DSV desk that is initialized as 0, and we will simply pass that in. DSV desk, does this create? No, it doesn't return an H result. And a descriptor handle, a CPU descriptor handle, meaning it's the start of where to place the descriptor itself. We will simply take our descriptor heap, which has a size of 1, and we will get the CPU address of the heap start, and we will make sure that this description gets stored there. Okay, we're almost done. Can't I spell this correctly? Oh, capital D. Okay, we need to specify a format here, which we already have, because we specified that in our actual resource initialization. We also need to specify a view dimension, meaning that we tell the system how to interpret this. Since we set it to a texture, we need to disable the MIP slices because there are no MIPs in this texture. And the flags are simply none. All right, let's see if everything compiles. Everything compiles. But we have not enabled depth buffering. So that's the last part we need to implement inside our pipeline. Right now we have created all the resources. We could use NVIDIA Insight to actually illustrate that we created the resources and bound them to our pipeline, but we will, we haven't bound them to our pipeline actually. But let's start out with actually enabling depth stenciling. We have currently disabled it. We want to enable it. We also need to set a format for our depth stencil, which is our format here. And we will compare each depth value with a less than function, and of course write whenever we need to. Okay, let's see if everything still compiles. Let's see, we have a debug problem here. Okay. Okay, so we need to do something when we do our draw call. That is, of course, binding the whole thing to the actual draw calls and pipeline. It complains that we haven't done that yet. And I mentioned it earlier that that is entirely true. We need to grab the CPU address of the handle for the depth stencil view, and we will get our descriptor heap here, and we will simply get the address for the CPU start, since we only have, or rather the descriptor heap handle, since we only have one depth stencil view, and it's stored right at the start of the heap. Therefore, we simply can grab the heap and its starting location. No need to offset it. Okay. The thing is that the render target here can actually take a description, or rather a handle, to our depth stencil descriptor. That is. So we can pass it that value. We would like to see if this sorts our error. It sorts our error. Right now we have a black screen though. So the problem is that we actually need to clear the depth stencil as well between every frame. So let's see. We usually do it while we clear the render target, and it's a graphics command call. Clear, clear depth stencil view, and we need to pass it our handle here, DSV handle, the clear flags, clear flag depth. Then we want to clear it to a depth of 1, and we do not do any stenciling, we do not do any kind of rects, so therefore the last values will be disabled. And here we go. We now have a proper sense of depth. Right now our front-facing plane here completely dominates the plane behind the actual one, which was to be expected because we actually defined these vertices here with an positive offset on the z-axis, meaning a forward-going direction, which means this is actually closer to our camera, which is placed on the negative z-axis. So therefore, everything looks quite all right. Let's try raising the camera a bit on the y-axis. And as you can see, we now have visibility of our two planes. Nothing is weirdly drawn. If we lower our camera a bit here, you will start to see the outline of a cube. So this is 3D rendering. What's left is actually defining the last vertices of this box. We will do one more side, as now we have better debugging of this. But what we need to do in this episode is basically wrapped up and good to go. We now have 3D rendering, and we might do the next video in terms of uploading the data and creating them on the actual default heap, since it's a performance optimization and resource management is part of DirectX, and it's a nice introduction to that topic. But let's try if we can define, maybe let's increase this to 18. Maybe let's do a macro, because then we don't have to box global box vertices 18 right now. Then we only need to change that value once. All right. Yeah, nothing will happen, I think. yeah, it doesn't know or it doesn't have any information about the vertices themselves, so they are basically skipped. But let's try defining the plane that's on the side here in our diagram here. That would be this plane here. Let's start on defining this one. Let's see if this is our y and x plane. This will be our c and y plane. Let's see, y, c. So if we are supposed to draw the vertex that is farthest away from this plane here, we would basically draw the one that is down here. That would mean a negative y value, a negative x value. X will be negative for all the vertices here, and a positive c value. Let's see, let's define 3 vertices here. 12, 12, 13, 13, 14, 14. And we talked about this being negative x no matter what, so let's make sure that every position is negative x1, and then it's negative on the y, and then the c was positive. Then this will have a positive y, but still a positive c value. Then this will have a negative y, a negative c value. And we will draw this in a different color. We will use the blue ones for this. Let's try that. Okay, as you might see, we do have a plane there, but let's see, maybe we need to turn our camera a bit by offsetting it a bit to the left, maybe even more, so that we can see the plane that we're working on. All right, as you can see here, we have our side. We will define the next part of this. Whoops, 15, 15, 16, 16, 17, 17. All right, so we will start by creating the one with a positive y, a positive c, and of course a negative x. Then we will draw the one with a negative c, a positive y, and a negative x. Then we will draw the one with the negative y, a negative c, and a negative x. And let's add a bit of green to this. There we go. There we go. So that's the other side. And yeah, you get the basic idea. Now it's way more easy to kind of visualize where we are drawing the vertices. I'll leave it up to you to complete this on your own if you want to do this method. Index drawing is way easier, so you can actually only you can skip all the vertices for each of the 6 planes, and you can simply just define every corner of the box, the cube, and through indexing you can use those corners multiple times in terms of drawing the actual triangles. So it's way more efficient. You don't have to store as many vertices, and you can reference a lot of vertices multiple times, which is usually the thing you need for drawing polygons. Anyway, I think this is it for this episode. We've covered a lot of different topics. We've covered a lot of ground, and we have actually fully functional 3D rendering. Congratulations if you stuck around this long. If you found any of this helpful, entertaining, inspirational, or something else entirely, feel free to like, comment, subscribe, or even support the channel. I'll probably do one more episode in terms of the resource management, in terms of uploading to the heap and maybe creating an index buffer. But that is all I have planned for this series. If there are certain topics that several viewers would like me to go over in terms of doing drawing and stuff on DirectX 12, leave a comment or drop by when I'm doing live streaming. I'll take it into consideration, and if there's enough requests on a certain topic, I might allocate time to do it. All right, but thanks for watching. Stay strong, focused, healthy, and keep on trucking. Hopefully I'll see you around. Bye bye. All right, let me just upload this to YouTube. All right. I now need to edit some stuff. Of course, I need to, let's see, we did part 16 last time. No, 17, so this is part 18. Depth buffering and 3D drawing. Great stuff. Okay, I'll be having a bathroom break and doing some stuff on the YouTube. So I'll be AFK for now.